All sounds are produced by vibrating bodies which send out waves. Most sounds are composed of irregularly shaped waves and perceived as noise, but regular waves are heard as a musical tone. The sound wave that is created when a musical note is played is represented by this function. Using a chart like this one, we can find the frequency of any note and plug it into the equation. If we let f equal the frequency of middle C, the graph of the sine wave will look like this. The frequency of a note is determined by these four factors. This relationship is represented by this equation. A thicker string vibrates at a lower frequency than a thinner string. As I turn the knob to the left, the string is pulled tighter, and as a result, there's more tension on the string, causing it to vibrate at a higher frequency. When I place my finger on the fret, the length of the string decreases, and as a result, the note is higher. When I halve the length of the string by pressing down on the fret, the resulting note is an octave higher. This is what Pythagoras realized when he uncovered the relationship between ratios and music. These ratios are also the concept behind the harmonic series. While we generally perceive a musical note as just one frequency, it is in reality not quite as simple as that. A series of overtones or higher frequencies are also produced by the vibrating body, in addition to the fundamental frequency, though they are not as evident to the ear. If I silently hold down the key an octave above C4 on the piano, or the first overtone, allowing the string to vibrate freely, you can actually hear the overtone when I quickly hit the C4 key. The presence and relative prominence of overtones is what explains why the same note sounds different on the violin, guitar, or piano. The body of the instrument determines which overtones are more or less prominent, and a combination of these is what creates the timbre or color of the sound. But can the appeal and emotions we feel as a result of music be broken down mathematically? Certain combinations of notes are certainly more pleasant than others, and when we examine the graphs of these waves, we can get an idea why. The major triad, for example, is very pleasing to the ear, and the graphs of these sound waves actually make up a geometric series. The ratio of the frequencies of the major triad is 4 to 5 to 6. The major triad is an example of consonance as the notes are in harmony. This harmony exists not only in our music, but in the workings of the universe, such as Jupiter's moons, Ganymede, Europa, and Io, that resonate in a 1 to 2 to 4 ratio, as if they're singing a low, middle, and high C. Dissonance, on the other hand, is used widely in music to create a sense of unsettling, eerie uncertainty, resulting from sound waves that rarely line up and do not sound pleasant to the ear, such as the tritone or devil's interval, as shown here. Considered to be the most dissonant interval, it is exactly halfway between the octave, and therefore, the frequency difference is equal to the square root of 2, an irrational number. Many have attempted to break down the appeal of certain chords or songs mathematically. Leonard Euler's Gradus Suavitatis ranks combinations of pitches into what he calls orders of softness. Dutch neuroscientist Jelle developed a mathematical formula to attempt to uncover what made feel-good songs effective. However, there may always be a degree of subjectivity to music that math will never be able to explain.